The broadcast is now starting. All attendees are in listen-only mode.
Hello and good afternoon, everyone. My name is Anna Zylik. I am with ICF, and we are the vendor working on behalf of the sponsors of Energize Connecticut to bring these passive house and all-electric trainings to all of you. So thanks for joining us today. These trainings are at no cost thanks to the sponsors of Energize Connecticut and are part of a partnership with Connecticut Passive House. Today's training will be recorded and we will post this online afterwards. Quick reminder that as a part of this training and workforce development initiative, we are offering a 75% cost reimbursement for individuals pursuing either FIAS or PHI professional accreditation. So this includes the cost of the training and the exam. And once you become certified, we will work with you to process the 75% cost reimbursement. So if you have any questions on that, please do not hesitate to contact us. Can you click on the next slide? Thank you. In addition to this no-cost educational training series and the professional accreditation reimbursement, the sponsors of Energize Connecticut also offer robust incentives for builders and developers. Next slide. So for those of you who choose to go all electric with your residential buildings or pursue passive house certification in multifamily projects with 5 or more units, the passive house incentive design for Energize Connecticut is shown here, and it includes pre-constructive incentives for feasibility studies and energy modeling, and post-construction incentives for full passive house certification. Next slide. Thank you. So the all-electric incentive is for both single-family and multifamily buildings. It offers 2 levels of eligibility with specific design and performance requirements associated for each, and has incentive amounts ranging from $1,500 per unit for multifamily to up to $10,000 for single-family homes. So our goal is for everyone involved in the construction of residential buildings in the state of Connecticut to be aware of these incentives. So if you are interested in learning more, please visit our website or contact us directly with our email that is on the slides. As for questions during today's session, please feel free to use the chat function throughout, and I will relay them over to today's presenter, Sarah. So with that, I will turn it over to Sarah from Newport Partners. Take it away.
Great, thank you so much. It's great to be here with you all. So as you know, I'm presenting on hot water innovations for decarbonization. And just a little bit about myself before we get started. I work at Newport Partners. We're a small consulting firm located in Davidsonville, Maryland. So we're kind of close to Annapolis, about 45 minutes outside of Washington, D.C. And we do various different projects. We do quite a bit of work with the Department of Energy on their Zero Energy Ready Homes program. We work with the Maryland Energy Administration, and we also do some work with NYSERDA up in New York State. So we're not using Slido because it's not working on my computer today, but I am interested to know who is listening in. So if you could take a second and drop in the chat, if you're a contractor, if you're an architect, efficiency program, that kind of thing, I'd be interested to hear from you. So I'll give you all a minute to respond. Let's see if we get anybody. If people are writing things and I'm not seeing it, let me know.
Okay, I'm seeing architects, people on the management advisory committees,
okay,
builders, more architects. Yeah, lots of architects, homeowners.
Oh, cool, great. All right, well, it sounds like we have a pretty good variety with lots of architects in there, so that's great to have all of you. Hopefully you'll learn some good tidbits about how to incorporate heat pump water heaters when you're doing building designs, things like that. So before we get started, here's a course overview of what we'll be covering in our 90 minutes together today. So first, we're going to take a little time looking at the why for decarbonizing hot water. it's always good to step back and look at the big picture for why we're putting so much time and effort into new complex technology. Then most of the webinar is going to cover the how. We'll go through heat pump water heaters, the main hot water decarbonization technology, and then cover a few other less common technologies and discuss the challenges and opportunities associated with heat pump water heater implementation. So a question I've gotten before is, will decarbonizing the United States really make a difference? And we'll skip over this one. And the answer is yes. So China produces the most GHG emissions per capita. The United States is second, and then India and Russia follow behind. So decarbonizing the US will really make a difference. The US is the 4th largest country by area, the 3rd largest by population, and as we saw just now, emits the 2nd largest volume of greenhouse gases of all the nations across the globe. Of course, China's the only country that beats us there. So this map shows all GHG emissions, including carbon dioxide, the most common greenhouse gas, but it also shows methane, nitrous oxide, HFCs, and CFCs, which are common household refrigerants. So in order to accurately show the impacts of these different types of greenhouse gases, we express them in terms of carbon dioxide equivalents. So each carbon dioxide equivalent is weighted by its global warming potential, and carbon dioxide itself is arbitrarily assigned a global warming potential of 1. So for example, methane has a GWP of 34, meaning that 1 kilogram of methane gas generates 34 times the warming effect as 1 kilogram of carbon dioxide gas over a 100-year timescale. So for your reference, nitrous oxide has a GWP of 273, and then HFCs and CFCs can range up to 15,000. So they have a very high impact, even though it's a small percentage of the total greenhouse gases emitted. But since carbon dioxide is the majority share, watching this more specific metric can give a good picture of relative GHG emissions over time. So looking at just the United States, we can see that our carbon dioxide emissions, specifically from fossil fuels, peaked at around 6 billion tons between 2005 and 2010. And since then, we've slowly made progress to decrease our emissions. Hopefully, we will continue to see this trend, especially as the current administration pushes for aggressive climate. A couple of these goals include the Department of Energy's all low or no carbon emission new construction homes by 2035, as well as the White House's goal of a net zero emissions economy by 2050. That means that we have about 27 years to undo what's been done over the past 150 years, which is daunting, but can seem more achievable if we break it down into small steps, one of which is what we're here to talk about today, decarbonizing our buildings, specifically domestic hot water. So how much energy do we use in buildings? Out of all the energy in the United States that's used annually, we use about 40% in our buildings, and that includes both residential and commercial. And a significant portion of the energy used in the residential sector goes to water heating. So let's see what number the group thinks that might be. So let's go back into our chat and ask, out of all the energy used just in US buildings, what percentage is used for water heating? So I'll give a couple seconds for people to type in their guesses, or if they know the answer. So we're looking for a percentage of energy used on water heating in our buildings. So if you can let me know when answers start popping up in the chat, that would be great.
10%, 15%, 60%, 40%.
Okay, so yeah, quite a variety. Thank you all for participating in that. So the answer is about 18%. So the 10%, 15%, we're getting close. So water heating constitutes about 18% of total energy consumption in US residential buildings. So it's also kind of interesting to look at the statistics of hot water energy use based on housing type. So in multifamily buildings, especially larger ones, the percentage is the highest. However, we can also see that the average amount of energy used for water heating per household is the lowest in multifamily buildings and the highest in single family homes. And that's due to the fact that detached single family homes typically have high overall energy use in general, making the domestic hot water energy use a smaller percentage of their overall load. So what type of fuel do we use for domestic water heating? That last slide showed water heating energy use broken down by housing type, and this one shows water heating energy use broken down by fuel type, which is a critical piece of information when we're talking about decarbonization. We see, as you might expect, that electricity and natural gas have the majority share of the water heating load. However, in 2020, we do see an encouraging statistic that electricity is close to surpassing natural gas as the most widely used fuel for water heating. This electricity, the orange bar there, includes both electric resistance and heat pump water heaters. And because of the potential for very high efficiency when you're using electric water heating, as well as regulations and incentives, the proportion of water heaters powered by electricity is likely to continue growing. So hopefully when we have our next set of bars on this slide, the orange bar will be farther over than our blue natural gas bar. So if we're switching our water heating over to electricity to aid in decarbonization, the next big question is, where does our electricity come from? So does switching to electric really help decarbonization? In 2021, nationwide, 37% of our electricity was generated using natural gas, 23% was from coal, 21% from renewables, and 19% from nuclear generation. And that 21% from renewables came mostly from wind, with a strong showing from hydroelectric as well. Based on our graph on the right here, we can see that solar is predicted to grow exponentially and overtake both of these sectors by 2050. So even though our electric grid today is not fully decarbonized, electrifying our homes does help prepare us for the greener grid that's on the horizon. Okay, so all those previous slides were about the first Y of water heating decarbonization, which is greenhouse gas emissions reductions. Now we're moving on to the second Y, though they're all interrelated, because this technology increases efficiency. So the first thing to look at here is the Uniform Energy Factor, or UEF. This rating is determined using a first hour rating, which is the amount of hot water that the heater will supply per hour in gallons, assuming that you're starting with a tank full of hot water. The rating varies among models depending on the tank capacity, the heat source, the size of the burner or element, and we used to use the energy factor rather than the uniform energy factor, but the UEF was developed to more accurately compare gas and electric efficiencies, which is really important part of the conversation that we're having now as we switch from gas to electric. So the data in the table on the screen comes from the AHRI directory, which is freely available online. It gives a pretty accurate representation of heating and cooling technology that's currently available on the market. Looking at this data, we can see a couple interesting patterns. First, the most common water heater in residential settings, a gas storage water heater, that top row there, is also the least efficient by quite a margin. So you can see the average rating is about 0.66. If you can't get away from gas, then we can see that tankless is your best option. It'll typically significantly increase your efficiency level beyond a gas storage water heater. Both types of electric resistance water heaters do have increased efficiency over gas, but we see that heat pump water heaters are the most efficient by a huge margin. You'll notice that all the other efficiency ratings are less than 1, and heat pump water heaters are able to break over that threshold, and we'll talk about why that is a bit later on. Our third why for water heating decarbonization is about saving money, what a lot of consumers care about the most. Here's a graph produced by AZEEE a couple years ago showing the life cycle costs for different types of water heating options. This graph shows the incremental cost for replacing a gas system at the end of its current service life, and this is in 2020 dollars. The data points include approximately 3,000 homes, and it looks at the direct capital and energy costs to the homeowner. And this is based on national level data, so regional discrepancies in gas and electric costs, which we'll talk about shortly, are smoothed out to a certain degree. So this graph, we can see, doesn't show electric resistant storage or tankless, but besides that, you can see that it roughly lines up with the previous slide, right? So electric heat pump water heaters are the most efficient and have the lowest cost, and then gas tankless and gas storage. So this study definitively shows that electric heat pump water heaters have the cheapest life cycle cost. However, as I previously said, it's worth noting that in some locations, the cost of electricity is so much higher than the cost of gas that an efficient gas water heater can sometimes have a lower lifetime cost to the homeowner than an electric heat pump water heater, which is a real problem. But as we move towards decarbonizing our electric grid, shifting our electricity production away from fossil fuels and towards renewable energy, we will start to see a shift where electricity becomes the more affordable option nationwide. And we already see this in places like Washington State, where the abundance of electricity produced with hydropower has made their electricity costs very low. So now we're going to go through a brief simplified savings example demonstrating this trend, which does account for regional variations in energy prices. So we're going to compare a 0.9 UEF gas water heater, which if we think back to that green table, this is a relatively high efficiency gas water heater, with a 3.7 UEF heat pump water heater. Both are Energy Star rated products, but you can see the immediate biggest difference here is the retail price, right? So the gas model comes in at about $500, while the heat pump water heater comes in at about 4 times that cost. So here we chose 4 different states to look at based on their relative electric and gas prices. These states have a very big variety in the cost of electricity, with a very low cost in Washington State, like we just talked about, and then a very high cost in Connecticut, where most of you probably are and are probably familiar with that. So in September, Connecticut of last year, Connecticut actually had the highest electricity cost per kilowatt hour in the 48 states, except for California at about 29 cents per kilowatt hour. But even so, we can see that the efficiency of the heat pump water heater is high enough that no matter the energy prices, the annual energy cost per year is cheaper for the heat pump water heater than for the gas furnace in every state. So that's that second column on our tables here. However, the question is the yearly energy cost reduction worth the high first cost of the equipment? For this set of water heater models, the answer is yes. It may change based on your set of heaters that you're comparing. After 10 years, you can see that every state does show savings for the heat pump water heater, meaning that over 10 years, you'll make up for the high initial cost of the heat pump water heater. This is especially true in states like Connecticut and Florida, where energy costs can be very high regardless of whether you're getting gas or electric, because your energy savings will be high in general. Another thing to consider when looking at the variations in the cost practicality of heat pump water heaters is the fluctuation in energy prices over time. So natural gas costs can be unpredictable because they have extenuating circumstances like geopolitical issues, supply, refinery expansions that can affect the price of natural gas in the future. It also won't be surprising to start seeing higher rates due to carbon taxes and the like in certain areas as well. On the other hand, projected nationwide rates for electricity from 2020 to 2050 are about 11 cents per kilowatt hour on average, which is roughly 10% lower than the historically observed rates from 1960 to 2019. And you can see that they sort of are predicted to even out with time. While the energy cost savings can vary regionally based on local utility costs, there are also rebates and tax incentives available nationally that can offset the high cost, the high initial cost. So until 2032, there's currently a nationwide federal tax credit that can cover up to your heat pump water heater installation or retrofit project, and that's through the Inflation Reduction Act. It's also worth looking into rebates and incentives available on a regional level, which are easy to look up. A lot of manufacturers have rebate searches on their websites. Energy Star also has one. So looking on Energy Star's site, I found that Rochester, New York, which was chosen because that's my hometown where I grew up, it has 2 utilities that offer heat pump water heater rebates. So they've got a $700 rebate from National Grid, $700 rebate from RG&E. And so both of these would cover almost half of your project costs. You can also stack the federal and local incentives to get maximum savings. A final savings method associated with switching to electric heat pump water heaters that we'll cover today is load shifting. So if you're not familiar, this is related to heat pump water heaters because it's only possible with electric systems. Load shifting works by integrating a battery with your electric system. So this is a very simple example on the screen. Basically, in the graph here, a battery collects energy from the grid during the night when it's typically cheaper and doesn't have to use energy from the grid during the day when it's more expensive for places that have fluctuating time of use rates. And so a lot of industrial buildings do take advantage of this cost differential by running night shifts at factories and things like that. But you can also take advantage of it at home with the integration of a battery. So you can also look to offsite batteries if you don't want to get one at home. Here's an example on the left of an offsite battery energy storage complex that allows for the collection and storage of electricity and a release of that electricity at a predetermined time. Now we're going to move on to the how of hot water decarbonization. So this is the majority of the webinar. We'll start by learning more about heat pump water heater technology itself. But first, I'd like to get a sense of how much experience the group already has with heat pump water heaters. So if you're still with us, if you can go back to the chat and type in if you've installed one before, if you're thinking about it, if you've never heard of them before, just sort of what your experience level might be. I'd be interested to hear that from the group.
I'm seeing some people are familiar. They've spec'd them. They've installed a few.
Okay.
They've only read about them.
Okay, so we've got a good mix of people who know about the technology, maybe haven't used it before, and then as well as some people who've installed a few of them. So that's great to hear. Thank you. So for those of you unfamiliar with the technology, we saw before that heat pump water heaters can have UEFs well above 1, which means that they give off more energy in the form of heat than they use. They do this by transferring heat from the air into water stored into a tank using compression technology, basically the opposite of how a household refrigerator works. Simply put, they move heat rather than create heat. So everybody stay with me here, but we're going to go back to our high school chemistry class for just a couple of slides to understand the underlying principles that make this technology possible. So it's not magic, it's thermodynamics. And there are 2 key concepts to understand. The first is to look at the ideal gas law, which is from a chemist way back in the 1830s, which for our purposes tells us that when a gas's pressure increases, so does its temperature. The opposite is also true. When a gas's pressure decreases, its temperature does as well. The 3 variables in the box there, the volume, amount of gas, and R, which is just a constant that makes the equation work, basically, the ideal gas constant. These things stay pretty much constant in the system we're looking at, so they won't affect this pressure-temperature relationship. So based on this rule, if you create pressure changes in a gas, you'll create temperature changes as well, right? So that's the first key concept, the relationship between pressure and temperature. The second key concept is that during phase changes, which is when a substance, in this case a refrigerant, switches from a gas to a liquid or a liquid to a gas, heat is either released or absorbed. So if you think about it, that makes sense, right? You need a certain amount of energy to go into a substance to make it vaporize, like when you boil water, and you need a certain amount of energy to come out of a substance to make it turn back to a liquid. That means that a gas going to a liquid releases heat, and a liquid going to a gas absorbs heat. So when we put these 2 concepts together, we end up with heat pump technology. We are using the first concept to force phase changes in the refrigerant, and the second concept to collect hot or cold air released during those phase changes. So let's look at this another way. This is a diagram of how the heat pump technology used in heat pump water heaters transfers heat from outside to inside using a refrigerant. We're going to start on the right side there. So in our loop, we have a refrigerant that is a liquid. Imagine that it's colder than the outside air. As it passes through the outside air, it will warm up. In fact, because the refrigerant has such a low vaporization temperature, it warms up enough to turn into a gas. Next, the gas passes through a compressor. And as we saw before, this increase in pressure will result in an increase in temperature. So now we have a high pressure, high temperature gas. This high temperature gas passes through the water that it's heating and starts to cool down again because the water is colder than the gas. It cools down enough that the gas turns back into a liquid. So when this happens, as we talked about before, energy is released in the form of heat. And then this heat is in turn absorbed by the water in the water heater, raising its temperature. Then the refrigerant, which is now a liquid, goes through an expansion valve, which brings its temperature and its pressure down so that the process can start all over again. So heat pumps can have an efficiency greater than 100%, which means a UEF higher than 1, because when heating, heat is extracted both from the work put in, which is the electricity used to run the compressor, and the heat drawn out of the environment, which is the heat that's coming out from the phase change of the refrigerant. So whereas other technology can only create heat from electricity put into the system, this technology gets heat from 2 different places. So when we start looking at how the system works when it's cold outside, the compressor turns out to be the pinch point in the system in terms of outdoor temperature. Because if the temperature of the vapor coming in is very low, the compressor has to increase the pressure in the system enough to be hotter than the water you're trying to heat. And the colder the vapor is, the harder the compressor has to work. So the technology in a heat pump water heater is exactly the same as a heat pump you would use for heating and cooling your home. But however, while heat pumps for space conditioning are often split systems, like the example we just discussed with an indoor and outdoor unit or coil, heat pump water heaters are more commonly produced as single package units, meaning that the whole heat pump is basically shrunk down and attached to a domestic hot water tank. So this different layout comes with a few additional challenges, which is why heat pump water heaters are not yet as ubiquitous as heat pumps for space heating might be. So the first difference, at least for unitary heat pump water heaters, is the location of the heat pump unit. So typically, heat pumps for space heating are located outdoors, while a unitary heat pump is completely located indoors. So while this is a benefit for the heat pump water heater because there's less fluctuation in the air temperature indoors, the problem is that there's less free air volume surrounding the unit, so the cool exhaust air has a much more dramatic impact on ambient air temperature. The second difference is that you're heating water rather than air, which means that your limiting factor in terms of temperature is the incoming groundwater, not the outdoor air. Third, while you're heating up probably to around 70 degrees or so indoors, water heaters are typically set to a much higher temperature than that, meaning that you need to get a lot more heat out of your heat pump water heater than you would for a typical space conditioning heat pump. Now, there are a few different ways to set up a heat pump water heater. They're most commonly sold as unitary systems, which is what we see on the left here. Out of the 3 configurations here, unitary is the most similar to gas and electric resistant storage water heaters that we have now, and typically the easiest to do a drop-in replacement for. In fact, there are some manufacturers developing heat pump water heater models that can plug into 120 volt outlets, which is just your typical outlet, rather than 240 volts. So all the plumber has to do is connect the 2 water lines. And that technology is, it's coming. It's still under development, but it's coming. And then we have the split system. This design places the heat pump equipment outside and the hot water tank inside, which does eliminate the sort of noise and cold air concerns that we'll talk about later. And then the third configuration here is for a central system. So this would be used by multifamily or commercial buildings for domestic hot water. And these systems get increasingly complicated the larger they get, but there are a lot of current research and development activities focused on central systems that they're trying to make easier to implement in multifamily settings. And we'll talk about a couple of those examples later on. So once you pick the configuration that you want to use, the next task is sizing. So this isn't really different from sizing a typical gas or electric storage water heater. You use the first hour rating, which is visible on the water heater's energy guide label, and make sure that the rating can accommodate the peak hour demand. So in the example above, the peak load is at about 8 a.m. So to enjoy your morning shower, the tank would need to store enough hot water to meet that need. Something to keep in mind is that the first hour rating for a heat pump water heater is a little lower than electric resistance or gas. This means that when you size for a heat pump water heater, the recommended tank size is typically larger than it would be for a gas or electric resistance water heater. Heat pump water heaters essentially take longer to heat water than those other technologies, so having a larger tank means that you won't run out of hot water and that the heat pump water heater won't need to switch to its backup electric resistance mode to provide the hot water you need. Another option besides using a larger tank is to let your heat pump water heater overheat your water, so you put the setting higher than, say, 120, and then you use a mixing valve to temper the water before it gets to your shower or faucet. To get a good idea kind of the sizing parameters for heat pump water heaters, the Energy Star Next Gen program requires heat pump water heater sizing according to the light blue chart shown here. So this can be a good general reference when thinking about how heat pump water heater sizing might differ from sizing for a typical gas or electric resistance water heater. So to illustrate this point, here we have 3 energy guide labels that come on water heaters. The one on the left is a 55-gallon gas water heater with a first hour rating of 91 gallons. In the middle is a heat pump water heater that has about the same tank size as the gas storage water heater, but it has a much lower first hour rating. And on the right, we have a heat pump water heater with a similar first hour rating to the gas water heater, but with a much larger tank. And so just for reference for these sizes, a 5-minute shower typically uses 10 to 15 gallons of water, depending on the water efficiency of your shower head. So different manufacturer teams are working on research projects to come up with solutions to this first hour rating issue. And the 3 biggest factors that they found so far to increase first hour rating are the sensor location, the inlet and outlet locations, and the mixing valve. So first, the sensor location. If you have a stratified tank where sort of there's colder water at the bottom and warmer water at the top, like the one in the image shown here, the sensor location is really important because the water temperature obviously varies quite a bit depending on where you locate your sensor. The second thing to consider is the inlet and outlet location for your cold water inlet and your hot water outlet. So in the heat pump water heater shown here, the cold water inlet is at the bottom of the tank and the hot water outlet is at the top near the heat pump. So this way, the hot water can start being delivered more quickly since the heater doesn't have to wait for the entire tank to heat up to the proper temperature before starting to deliver the water. And then finally, a third strategy is to heat the water up to a higher temperature than usual and include a mixing valve with cold water to prevent scalding from that water. And studies have shown that this mixing valve method is typically the most effective strategy to increase the first hour rating of your system. So before moving on from this, one more thing to note is that there's usually a trade-off between first hour rating and uniform energy factor. Heat pump water heaters with a higher UEF tend to have a lower first hour rating and vice versa. So next, we need to pick the right place to install our properly sized heat pump water heater, right? So 3 things to consider when picking the best location are temperature, amount of space, and proximity to living space. Heat pump water heaters run most efficiently in warm spaces with plenty of air volume. Looking at 4 different areas where a heat pump water heater could be located, the basement, laundry room, an attic, or a bedroom closet. The best space is in a basement near the furnace where it is warm and there's lots of space. The next best space, which is also very common, is in the laundry room. It's already warm and humid in here, which helps the heat pump water heater to run efficiently, but it can be lacking in air volume. So the heat pump water heater will absorb the excess heat and moisture and keep the laundry room from having moisture issues. An unconditioned attic has the opposite problem. So there's a lot of space there, but the temperature can fluctuate a lot. And one of the worst spaces would be a bedroom closet where it's very close to living spaces. Although being in conditioned space would help the heat pump water heater to run efficiently, it would also probably bother the residents with the noise and the cold air that it gives off. So now, if the video works properly, we're going to go through a couple of videos showing a real heat pump water heater installation done by a local contractor in the state of Maine. So the U.S. Department of Energy went to the job site here and recorded the installation process and chatted with the installer to get a good on-the-ground perspective on what challenges there might be during the installation process. So the chosen home here was a 160-year-old Victorian home with a lot of preservation work already done on different historic elements of the house. And then so as not to interfere with any of that, the design team chose to install the new heat pump water heater where the old water heater was in the unfinished basement. So first we'll hear a brief introduction to the project with Adam LaChance, who was the local installer.
Now, could you walk us through the most important steps for installation that are unique to heat pump water heaters? Versus the fuel system, with the existing system, you utilize the oil boiler the pump in the system, the oil burner that heats the water. So we did have to have an electrician add a 240 volt circuit to provide the electricity to the unit. Otherwise, it's really straightforward. We connect the cold water inlet from the tank to the existing cold water pipes, connect the hot water outlet to the existing water pipes. In this case, we're going to add a few extra valves so that we can turn off the oil water heater, but allow for it to be used in the future if there's a need for that. Okay. And I guess the only other thing we will be connecting is, because it's a heat pump water heater, it dehumidifies and makes condensation. So we have to install a condensate drain to the floor drain in the corner here. So as the unit runs, removes the moisture from the air in the basement, it has a place to drain. So our existing unit is going to pretty much be used for redundancy in any case we have something that happens to this specific heat pump. Yeah, it's likely never going to be used again.
All right, so that was our intro to kind of the installation situation going on there. And then next we're gonna see him preparing, preparing the copper piping for the heat pump water heater. So here we go. So first we see him prepping the copper pipes by putting the fitting on the end to prep for a pipe union so they can add in a shutoff valve connected to the heat pump water heater. So there he goes, adding in that shutoff valve so that it can be easily connected and disconnected. And then next, we'll need to connect these heat pump water heater pipes. Just pause. Oh, next slide, sorry about that. Next, he's gonna connect the heat pump water heater pipes to the existing pipes in the basement. So first, we need to drain out all of the water that's in the pipes now. And then he'll measure and connect the new pipes at both ends. So first, he's running a line to the outlet, draining out the water. And another fittings installed there for emergency shutoff purposes. Okay, and then finally he's checking to make sure that there are no leaks between the systems. Okay, so that was connecting the pipes from the old pipes to the new heat pump water heater. So next, and finally, he installs a condensate drain line. So this connects from the side of the heat pump water heater there, and then will run along the floor over to the drain in the corner. So you'll see that happening in a minute. Okay, so connecting that, just having it run over the various bumps that you're going to have in an old basement. Fixing it to the floor so it's not a trip hazard there. And then there it is over the drain in the corner so that it will release the water. And the last note that you saw there was that they left an air gap so that you don't end up with water running back towards your heat pump water heater, which is what you don't want. Okay, and then we'll hear from him one more time.
Now, as far as challenges that you might have incurred while doing this installation, are there any that you could tell us about? Yeah, everybody down here saw that being an existing home with existing piping that was already full of water, a little bit of a challenge I had was getting the water out of all the pipes. Fortunately, I used
Very nice. That I totally get that with the water being in the system, it could be a hassle to get the piping connected the right way. In the timely manner.
Yeah.
So absolutely. Now, what advice can you offer to other contractors in the area that may be dealing with these heat pump water heating systems as far as installation goes?
I would recommend them in most scenarios. I mean, they're extremely efficient. They're easy installation. They're reducing your carbon footprint, and the rebates available in Maine make them very cost effective. So if you want to save money and reduce fuel usage, then they're ideal.
All right, so
Now,
that was an example of an on-the-ground water heater installation. So hopefully it was interesting and informative. Quick look at what happens on the ground with a typical heat pump water heater installation if you haven't been present at one before. And then next, aside from air source heat pump water heaters, which is what we've been talking about so far and what we just saw the installation of, there's a few other good options for increasing your water heating efficiency, which we're going to talk about now. And the first one is these tankless water heaters. And there are two different options for tankless water heaters. Obviously, there's gas and there's electric. So the pictures on the slide here are actually from one of Newport's office buildings. So we have an office here in Maryland, and we also have one up in Schenectady. So this is in that office in New York. And so that building has 3 stories above grade. It's kind of a townhouse that has a basement built in kind of the 1930s. And it's all brick with very thick walls. And the commercial office space is on the first floor, and then the second and third floors have apartments. So this building originally had a gas boiler and a gas water heater located in the basement and a gas fireplace on the second floor. Last year, we had to replace the gas water heater. It stopped working, and this is a pretty common scenario for older buildings, especially in the Northeast, that they're kind of completely on gas. So we started looking at different options. And a heat pump water heater, unfortunately, was crossed off the list because the product cost and the installation would have been very expensive, and the distribution system in the home wasn't really set up for it or in the building. So it would have been an expensive solution for very slow hot water. But of course, we were conscious of trying to be more environmentally friendly, so we looked at some tankless options. And since we already had a gas service, if you already have gas service and a gas water heater is the best option, then tankless is a good way to go. So it is more expensive than a traditional gas water heater with storage, but it's much more efficient, as we saw before. Unfortunately, for many retrofit situations, this is kind of the best you can do. So it's not complete decarbonization, but it does help a lot. And the reports are from our New York staff that it's working really well for them, providing their hot water even when it's cold, things like that. Another option, which is less common, at least in the United States, is a solar-assisted heat pump water heater. So this shows the cover photos for 2 products. One is British and the other one is Portuguese. And solar-assisted heat pumps work by combining solar energy from thermal solar panels and heat pumps to produce heat. So basically, it's adding something on to help your heat pump work a little more efficiently. And there are different configurations and types of solar collectors that are used with these systems. So the most common types of collectors used with solar-assisted water heating are evacuated tube collectors, and which is on the left here, and then the one on the right is the photovoltaic thermal or hybrid collectors. So on the left, we have the evacuated tube collector. These are the most efficient collectors available and work well in most climates, including colder ones. Each evacuated tube there is similar to a thermos in principle, so a glass or metal tube containing the water or refrigerant is surrounded by a larger glass tube, and the space between them is a vacuum, so very little heat is lost from the fluid. The fluid running through the inside tubes can absorb that solar radiation directly, but because of the vacuum between the exterior and interior tubes, the fluid is able to absorb all the radiation from the sun without releasing any heat energy to the ambient air. So in warmer climates, this fluid can be watered directly. But in colder climates, you would want some kind of refrigerant because you don't obviously want the fluid to freeze and then crack your collector. These collectors can work well even in overcast conditions and operate in temperatures as low as -40 degrees Fahrenheit if you do use the pressurized tubes with a refrigerant. And the individual tubes can be replaced as needed, which helps with the cost effectiveness because these collectors are typically very expensive. So being able to just replace the smaller tubes one at a time can help with that. And then the photovoltaic thermal, or also called hybrid, are less efficient. So this is the image on the right side, but they're often much more cost effective because the technology isn't as expensive. So these work by combining PV solar cells and thermal panels. And basically, while the evacuated tube collector on the left are used exclusively for water heating, PV thermal panels are a hybrid. So that means that they're able to convert solar energy into both electricity and domestic hot water at the same time. So this is a real-life example of a solar PV thermal system, so the second type we talked about. In the image on the left, you can see the photovoltaic panel on the outside wall of the house is to the left of the heat pump, so that black panel there. And then this heat pump to the right there is used for the home's space heating and cooling, so it's not related to water heating. And then the right image is the water tank in the home's basement, which connects to the PV thermal panel outside through the wall. Here's another example of a different type of setup. So this is a forced convection solar assisted heat pump water heater. So this is an example of a solar assisted heat pump water heater using an evacuated tube collector. And this schematic actually comes from a recently published study on an innovative solar assisted heat pump system, which is designed to provide good performance both when it's sunny and when it's cloudy or nighttime, things like that, which is a current limitation of both solar thermal and solar PV hybrid systems. So the system's innovation lies in that it uses a blower fan, which enables forced convection during partial sunshine and diffuse light conditions. So forced convection, like natural convection, and a regular solar air dual source heat pump extracts the ambient thermal source to the refrigerant flow. So this heat pump, for example, has 3 different operating modes. One is the solar air source natural mode, which is basically the system works through the day while solar radiation is high, enabling the evaporator to gather solar energy and heat from the surrounding air through natural convection. So that's kind of your typical, the mode that basically makes it function as a typical solar assisted heat pump water heater. And then the solar air forced mode also works through the day, but when sunlight is not fully available, the evaporator uses forced convection to absorb heat from the surrounding air as well as solar energy. So, and then when solar radiation is totally absent during dusk or night hours, the system uses just air source forced mode, as the evaporator absorbs only ambient thermal energy from the air via forced convection. So that's kind of similar to how the heat pump itself usually works, right? And then here's another interesting option. This is an integrated space conditioning and water heating scenario. So in the scenario, we have a large heat pump that generates both the home's heating and cooling as well as the hot water. And so having a larger heat pump can mean that you can have a more efficient heat pump that requires less maintenance. But on the downside, if it goes down, then everything goes down, right? Your heating and cooling for your space as well as your water. So the benefits of this type of system is that they can be much faster to produce your hot water, and there's much more flexibility for the tank size and location. Unfortunately, these systems aren't really available yet as packaged systems in the United States, and they're kind of expensive and complex to implement because of piping layouts and refrigerant circuits and system controls, and you need 2 different water tanks to provide both space heating and space cooling. But here is a real-life example of one of those integrated space conditioning and water heating systems. It's located in Washington State in a relatively mild marine climate. There's a combined air-to-water heat pump for space and water heating with a 50-gallon tank located in a conditioned basement. And there's also an electric tankless backup water heater in case the heat pump can't keep up during a cold snap. So in the image on the right here with the red labels, you can see two separate water tanks, right? One is for DHW, domestic hot water, and then the one on the left is for space heating and cooling. And the builder was very happy with how the system turned out, and he said, we love it. We can do heating, cooling, domestic hot water for about $30,000, which is $10,000 less than local installers are doing for less efficient systems. So he was very pleased with how this turned out. And then here's one more example of a home that implemented one of these integrated systems. This one's also located in Washington State in a mild marine climate, but these tend to work very well. So the image on the right shows how the home is using radiant heat for space heating. So you can see that this is a way to distribute hot water produced through the house in the form of space heating by running it in pipes under, it can be under your floor, which people tend to like because it can keep your feet nice and warm in the wintertime. But anyway, so you can see that while integrated space and water heating systems aren't offered as packages yet in US markets, there are several high performance builders who are working on specifying and creating custom systems to increase HVAC and water heating efficiency in the homes they're building. So challenges and opportunities. We briefly touched on this before when we were talking about the best place to put your heat pump water heaters. But here we'll talk about the challenges and opportunities for improvement that we have with heat pump water heaters.
Sarah, there are a couple of questions.
Yeah.
Maybe I can throw them at you before we move on.
Yeah.
Based on that image you had, there was a question that maybe you probably answered now. Can heat pump water heaters be used for radiant floor heating?
Yes, so that's a good question. That's exactly what this image shows here. So this would be a situation where you can never have the water that comes through the radiant floor go back into your water system, right? But if you have a heat pump water heater that's got either a second tank with a slightly lower temperature water, or there's a tempering valve, then you can send off your domestic hot water to your heating pipes for your faucets and things like that, and then you can send water also through your radiant floor heat. So it is able to provide both. Yep.
Okay, and is the single solar panel intended to supplement electric power only or power fully?
I think they're probably referring to this example back here.
Yeah.
So I am not sure about the answer to that question for this particular case study. I know that there are systems that can be fully solar powered. Those typically would use the evacuated tube collector method though, because it's a lot more efficient. But so my guess is that probably this one is just supplementing the heat. So it's solar assisted heat pump water heater. So they're also using electricity in the compressor to use the heat pump cycle to heat the water as well. So this one's probably using both is my guess.
Okay, one more kind of general. What is the efficiency of a heat pump water heater compared to on-demand electric water heaters?
Yeah, that's a good question. So if we go all the way back, let me see. I don't know off the top of my head, but if we go all the way back to our green table here, so we've got heat pump water heaters. Average efficiency is about 3.4, and then electric resistance tankless is the next best option, and they average about 0.94. So they are very good if you can't get to a heat pump water heater. They are a very good option.
Okay, thank you. One more that just came in, and then we can probably continue. Can heat pump water heaters run off batteries in a standalone solar PV system?
Can you repeat the question?
Yeah, can heat pump water heaters run off batteries in a standalone solar PV system?
I believe so. I mean, it just depends probably on the size of your battery and the capacity, right? Because if it can provide the amount of power you need, it's just an electric system. So my guess is yes. I can't say that I'm an expert on solar installations and distributions and things like that, but I do know of with our work with the Zero Energy Ready Home program, I do know of some examples of homes that are fully off the grid and they use a solar system with battery backup, and they have heat pump water heaters. And I don't know if the heat pump water heater is running only on the battery at any time, or if there's always some solar coming in. I'm not sure about that, but theoretically it should be possible. Yes.
Okay.
All right.
Thank
you for bringing up those questions. Thank you guys for continuing to ask good questions. We'll look forward to answering some more later on, but we'll move on now to the challenges and opportunities associated with heat pump water heaters. So we briefly touched on this before when we were talking about the best place to put heat pump water heaters, but here we'll talk about the challenges and opportunities for improvement that we have with heat pump water heaters. So they are noisy, they let off cold air that can affect ambient room temperature, they have maintenance issues, sometimes they struggle with different climates, and they need a lot of space. And so climate and space are definitely the biggest challenges of the 5. So as we talked about before, when we're talking about the heat pump cycle, one of the limiting factors for a heat pump water heater's efficiency is the temperature of the incoming groundwater. And so this graph here just sort of shows at one site over a year, the average temperatures of the incoming cold water. You can see it fluctuates seasonally. And so all water heaters must expend more energy if the water coming into the tank is colder, right? So colder air temperature makes the ground with the water pipes in them colder. The water inside the pipes gets colder as well, with a small delay typically. So colder groundwater temperatures may pose a threat to the performance of heat pump water heaters in cold climates because the system must heat colder water, which requires more work. This is less of a concern in warmer climates. So heat pumps and heat pump water heaters typically work best in moderate climates. This map from the Building America Solution Center from the Department of Energy shows 5 general climate regions. You can see that the southern half of the US and the West Coast are mild, but a large portion of the US is cold and very cold. So new cold climate heat pump technologies are being developed. In fact, the Department of Energy has a cold climate heat pump challenge going on right now. In the Department of Energy Zero Energy Ready Home program, which I was just talking about, we do see heat pump water heater installations all over the country. The 2 combined space and water heating examples in Washington State we looked at just now were Zero Energy Ready Home projects. But regardless of the climate, and particularly in cold climates, it's important to locate the heat pump water heater in conditioned space because most units need a temperature range between 45 and 120 degrees Fahrenheit to operate effectively. So in single family homes, water heaters are tucked into basements, crawl spaces, garages, attics, in their own closets where this temperature requirement can be met. So in the Northeast, where it's cold and there are basements, a conditioned basement is a very good location. In the Pacific Northwest, since outdoor temperatures typically do stay close to this range, garages are ideal because your unit can stay protected while staying at the right temperature. In the Southeast, where they don't build basements, garages and conditioned attics will also work. And then if we think about it, location is especially an issue in multifamily buildings where floor space is very valuable. So in Southern California, we have seen heat pump water heaters actually outside. The unit it serves on a balcony in sort of a mechanical closet, also because the temperatures there can be very mild. So in addition to staying within the most efficient operating temperature range from 45 to 120 degrees Fahrenheit, heat pump water heaters also need sufficient air volume to work effectively. The heat pump unit in heat pump water heaters take in quite a bit of volume of air to run the whole heat pump mechanism while operating at full capacity. So if your room is less than about 700 cubic feet, you probably will need some workarounds because the air will either get too cold in the space for the outlet, or if the outlet is ducted, you'll end up with negative pressure in the room, and the heat pump water heater has to work harder and harder and harder. So this air volume for best heat pump water heater performance, 700 cubic feet, this volume can vary, and each unit you buy on the manufacturer instructions should have that sort of minimum rated air volume required. So there are 3 typical ways around the space issue. The first one on the left is just a louvered door. So this allows air in from other spaces in the building. So basically just expanding your room to include the rooms around it. And then second, you can duct your cold air outlet to maintain the air temperature in the room. And then, like we said before, you'd need to create an air gap under the door so you don't end up with that negative pressure problem we talked about. And then third, you can duct the inlet and the outlet, so then you don't have to do anything with your door. And this provides steady flow of conditioned air to the heat pump water heater and then extracts the cold air, probably outdoors. Here's an example floor plan of 2 of those options in action. So at the top, the Unit A living room has a closet with a louvered door to provide enough air volume to the heat pump water heater. So this could result in some cold air blowing out into the living room from your heat pump water heater exhaust, but it is the cheapest option because all you have to do is switch out the door. There's no additional ducting required. But then you can see in Unit B on the bottom, they use a ducted to outside configuration, which provides the same airflow to the unit, but does not blow the cold air back inside. Instead, it goes back outdoors. So this will prevent any comfort issues inside the kitchen, pardon me, inside the kitchen where it's located, but can be more expensive because of that additional ducting cost. Here is a case study example. This is another zero energy ready home. This is an example of a project that was built with a heat pump water heater in the utility closet laundry room. So this system is provided with enough space to operate because it shares the room with other appliances, and it also has a duct to better circulate the cold air out of the room. So as such, this unit is able to stay in heat pump only mode for most of the year without causing any discomfort to the residents. And the builder mentioned that in another home, they built the same, pretty much the same home, but they have their heat pump water heater in an unvented utility room. And the cooler air has created discomfort issues in colder months in upstate New York. So it switched over to electric only for 6 months out of the year by the homeowner. And this has been going on for at least 5 years now. But they mentioned the newer home shown here has been occupied since 2021, and they haven't had any complaints from the homeowner, and the unit is running in heat pump mode year round, so the ducting worked, and that was great. And then this is just a close-up of the specific heat pump water heater equipment used in that project. So it was a 50-gallon Energy Star Ream Performance Platinum hybrid heat pump water heater, and there it is located in the laundry utility room on the side there. So climate and space constraints, the 2 first challenges we covered have the biggest impact on heat pump water heater performance, but there are a few other challenges that can be annoyances for homeowners. The first is noise. So because they suck in and blow out air, right, like a fan, heat pump water heaters can be noisy, which is an obvious issue within a multifamily unit or single family home without a basement or garage. All the units can be switched to the electric resistance mode, which does eliminate this noise, but obviously greatly reduces the unit's efficiency because you're just going back to an electric resistance water heater. The units are currently not rated for noise, although some of the units do have like a decibel rating, where the lower the number, the quieter the unit is. And there has been some discussion around creating a decibel standard for this equipment, but it hasn't come out yet. Sometimes there can also be noise caused by vibration of the unit. So if your tank happens to be by a stud, often that noise is going to show up in other spots in your house. So we heard from an installing contractor, they often will put vibration earthquake straps or rubber pads against the base and walls of the unit to help alleviate this noise source if they notice it becoming a problem. The next annoyance for homeowners is maintenance. So heat pump water heaters do need maintenance and filter cleaning or replacement according to manufacturer specifications, which can range from every month to every 6 months, but that does require access to each unit on a regular basis. So this is tough for multifamily, where tenants or renters aren't responsible for maintenance of their unit. The property manager has to make sure they have regular access and they can worry about bothering the tenants and things like that. So on that note, the last big challenge we'll cover is how to use heat pump water heaters in multifamily buildings. This can be quite a bit more complicated than in a single family home setup and require a lot more planning than it does for single family homes. So in multifamily buildings, there are a few basic configuration options for air source heat pump water heaters. You can have individual heat pump water heaters in each unit. You can have a heat pump water heater serving a couple of dwelling units kind of spread around the building, and you can have a fully centralized system. So this first example is of the individual heat pump water heater configuration where one unit is shared by sets of 4 dwelling units. So this is kind of an in-between choice for multifamily buildings that don't require a heat pump water heater in every unit because maybe the units are very small and have 1 or 2 occupants. And it also doesn't require a fully centralized system, which can get very complicated. So you can see in the plan on the right here, there's 1 heat pump water heater under each of those blue arrows, and there are 2 units on this level of the floor plan and then 2 units on an upper level, meaning that each heat pump water heater is serving 4 units total. So cost is the greatest benefit here, right? The reduced first cost for the equipment, reduced plumbing costs, reduced maintenance and replacement costs, since there's only 1 for all 4 units. And the way they've laid it out, there's an exterior utility door so that property manager can actually check on the unit without going into the tenant's apartments. But then the disadvantages do include the increased likelihood of running out of water, right? Because you're serving 4 different units at the same time. Your failures are going to impact more people, and then it can have a lower efficiency due to coincident hot water loads. So if everybody all at once is taking a shower in these 4 units, then it's probably going to switch on to electric resistance mode to keep up with the hot water demand. So our next 2 examples of multifamily buildings with heat pump water heaters are fully centralized systems. The first one here is called Bayview Towers, and it's located in Seattle. And it is the result of a 10-year-long collaboration between a research firm, a federal utility agency, and a manufacturer. So it's a very big project. And it's the result of an attempt to develop kind of an easy-to-install commercial heat pump water heating system for multifamily buildings that can be easily replicated on other projects, which doesn't currently exist. So the Bayview Central Heat Pump Water Heater System includes a Mitsubishi QAHV heat pump, primary storage tanks plumbed in parallel, and a temperature maintenance system that, since it was retrofitted, uses old electric resistance tanks from the old system as the swing tanks, which is kind of interesting. And then the Mitsubishi QAHV heat pump uses carbon dioxide as a refrigerant, which is interesting as well. It's a natural refrigerant with a global warming potential of 1, like we discussed before, so much lower than those CFCs and HFCs that were another small piece of our GHG emissions. And it's a great candidate for outdoor installations in cooler climates. So the next example, Zero Place, uses ground source heat pump technology rather than air source, like in Bayview. So this is a recently completed mixed use building with 46 apartments and 8,000 square feet of retail space on the first floor. So the ground source central system uses vertical wells confined to the building's footprint so that they would save money on buying any extra land for that. This system has 4 162-gallon water tanks lined up in the basement, which you can see in the image on the left-hand side. This is actually twice the capacity that they really needed to meet the building's load, but it was implemented this way for redundancy so that they would ensure they never ran out, and then if one of the tanks went down, they'd still have enough water. So tanks 1 and 2, the tanks on the top in the image on the right, which shows their interconnections, tanks 1 and 2 are marked at 121.8 degrees. They preheat the water, and then tanks 3 and 4 take the water the rest of the way. So it's sort of a layered system in that way. So water heating, space heating, air conditioning are actually all integrated into this one heat management system, like we kind of discussed previously in the single family home examples. And then water is the heat transfer medium throughout the building. So during the cooling season, heat pumps in each dwelling unit extract heat from the air, and they put that heat back into the water loop, where it goes back into use by the heat pump water heater for domestic hot water. And then if there is excess heat in the summertime, it can also go back into those ground wells. And this is the second multifamily building in New York State to use this strategy, which is called a common ground loop. But it's 4 times bigger than the first one, demonstrating scalability of this technology. So in total, this system uses about 18% of the building's energy use. If we think back to the beginning of this presentation, 18% of energy typically represents the energy used for only domestic hot water heating in residential buildings. But in this example, that 18% represents the energy used for both water heating and space conditioning, which are two of the typically largest energy loads a building has. So these on the screen here are some of the various manufacturers that sell heat pump water heaters, and they're all working to innovate and improve the technology. And they're all manufacturers that are part of the Heat Pump Water Heater Manufacturers Roundtable, which is hosted by the Advanced Water Heating Initiative and the New Buildings Institute. And so I'll just quickly go through some examples of models that have popped up recently at those meetings. For Rheem, we have the new Rheem Pro Terra models, which retail between $1,900 and $3,100, depending on their water tank capacity and how much compressor power they need to heat that water. It appears that for now, the way that they're able to reduce their voltage from the typical 240 down to 120 is by dropping the electric resistance back up, which could be an issue in a colder climate. But then we have Eco 2, and their claim to fame is that they use carbon dioxide for their refrigerant, like the Bayview Tower central system we discussed earlier. One thing to note about that is because of carbon dioxide's high operating pressures, they typically have a split system design where the heat pump itself is outdoors and then the water storage is indoors, so that if there's ever a problem with that high operating pressure system, then there's no safety concern inside the house. A.O. Smith next. So their strategy right now is to focus on the ease of installation. So they design their heat pump water heaters with no connections on the backs or the sides. So they have a zero clearance design, and then they have connections for the water inlet and outlet on both the top and the front. So depending on where your old water pipes were, it makes it a little bit easier to use these as drop-in replacements. Bradford White, also thinking a lot about how to ensure that heat pump water heaters get installed in a way that will allow them to operate as efficiently as possible. So a bad install can take away all that efficiency you gained from your new unit. And so they provide QR codes right on each unit that have specific instructions for the installing contractor, so that you make sure that everything is done correctly, especially if you have a contractor who's never done a heat pump water heater before. And then Ice Air, they've been working on new cold climate heat pumps, as the name implies. So they're operating out of Mount Vernon, New York, and their series are being tested down to -13 degrees Fahrenheit and are shown to provide hot water at their highest efficiency even at those extremely cold temperatures. And then Nile is focusing heavily on innovating modular heat pump water heater systems that can be used in commercial and multifamily applications that are scalable based on the size of the water heating mode. So you can add modules up the bigger your building gets in order to meet your hot water load. And there are lots of other great heat pump water heater products out there as well. And more innovations are happening with this technology every day. So Energy Star has, in fact, just developed a cold climate rating for their air source heat pumps, and they're looking at developing a similar certification for heat pump water heaters. So I'd also like to point to some additional resources for folks looking to get more involved in the heat pump water heater scene. The Advanced Water Heating Initiative, which I just mentioned, has working groups on various topics related to heat pump water heaters, including commercial connectivity controls groups. And Energy Star also has a manufacturer action council dedicated to providing training, marketing, and sales channel engagement. Energy Star also has a heat pump water heater education page shown on the right here, which you can get to with a quick Google search. So heat pump water heaters are a relatively new and evolving technology, and it's normal to have a lot of questions about evolving technologies like this. So if you do have any questions about the content we presented today or about anything else related to heat pump water heaters, please don't hesitate to reach out to myself, our Newport partners with questions. Our information is on the screen there. And that is all I have for you today. So I'd love to hear if there are any more questions.
Yes, there are a couple more that have come in. So let's see. Is climate a greater challenge for heat pump water heaters, or does it equally affect all kinds of water heaters? The climate.
Climate, yeah. So, I mean, it's definitely going to affect all kinds of water heaters, right? Because the issue is that your incoming groundwater is cold. For heat pump water heaters, it can be a little bit more challenging, specifically because of the temper differential we were talking about. So similar to when it's really cold outside and your heat pump doesn't operate as efficiently because it's harder to extract heat from that. It's harder to heat up your water in your heat pump water heater if you're using colder water to begin with.
Okay. Does a heat pump water heater create a vacuum in a fully sealed house?
So it depends. It can create a very small vacuum if it's in a fully sealed room. If it's in a house, it probably won't have that much effect because the draw isn't that high. But if you're in a fully sealed house and you have a louvered door or you've got that air gap below the door and you have a heat pump water heater in the room, then that is plenty to make sure that you don't have any issues related to that.
Okay, thank you. Another question. Can a ducted heat pump water heater have its ducts directly connected to ductwork of an ASHP ductwork?
Yes. So I think what the question's asking is can you basically connect your typical HVAC ducts in with your heat pump water heater ducts? And so if you're ducting your heat pump water heater, the supply air can come directly from the same ducts that are supplying air to the rest of your house that are conditioning the house. But the exhaust air, obviously, you would want to go with, if you have a ventilation exhaust system, you would want it to go there instead of back into your, in the wintertime, you don't want the cold air going back into the ducts supplying the heat for your house, right? So, but yes, you can connect all those ducts together.
Okay. Another one that came in, are all of the heat pump water heaters on the market, with the exception of Eco 2, are they using an R401A? And are you concerned with the phase out of that refrigerant?
That's a great question. I'm not positive if they all use R401A. I think for the most part they do. So there's a lot of research going on right now to phase out these high global warming potential refrigerants. So in general, I actually think that's a positive thing, right? Because we want to get rid of these super high global warming potential refrigerants. The only issue is that we're still working to develop heat pump cycles that work well with different types of refrigerants. So I wouldn't say I'm concerned about the phase out, but that we do still have some work to do when it comes to phasing in the more environmentally friendly refrigerants.
Okay. I think that was the last question, unless anyone has any last minute questions they want to submit. No, I don't think so. Okay, so I guess we can wrap it up here. And yeah, thank you, Sarah, for this great presentation. Yeah, just a reminder again, this will be recorded and posted online, and we'll send everyone an email to a link to the recording once that's available. And yeah, thanks again to the sponsors of Energize Connecticut for bringing this passive house and all electric training, and that's it. Thank you, Sarah.
Thank you.
All right, have a good rest of the day, everyone. Bye.